So we're going to keep talking about a couple of really common reactions for organometallic catalysts in industry and other processes that are really important for all the materials that we use today in all the chemical industry. So what I'm hoping you get out of this is not, you don't have to memorize the mechanism, but just so that you can see how all the things that we've learned so far in the last 5 weeks sort of come together, and you can see all the different individual steps. And since you know a lot about each of those reactions now, since we covered that first, then you have an understanding of how that reaction happens and what are the factors that dictate the kinetics of that reaction, what makes it more favorable in either direction. And so when people actually study catalysts, you try to, you can never prove a mechanism, but you try to propose a reasonable mechanism based on what we now know about reactions that organometallic compounds can do. And then, you can do kinetic studies to try to figure out what rate determining steps are, for example. And now for example, if it's dissociation is a rate determining step. You want a bigger phosphine or a bigger group on there to help promote dissociation. There are other things you can use, different metals that may promote dissociation, ones that are more labile. If you want something to be more favorable for oxidative addition, then maybe you want a smaller group, smaller ligand groups on it. And so now you know all those things so that you can help improve catalysts once you propose a mechanism that's reasonable and all the evidence seems to support it. So the next reaction we're going to look at is hydroformylation. The net reaction takes alkenes to aldehydes. So when we did Ziegler-Natta catalyst, I brought in, sandwich bags and plasticware, Tupperware, and that's what you get from Ziegler-Natta type catalyst. When we did Monsanto acetic acid process, I brought in vinegar. So this one is not an obvious one for me to bring in something that you see every day, but this is actually the largest scale reaction that's done with homogeneous catalyst. And it's done on the order of 6.6 times 10 to the 6 tons, so it's basically over 6 million tons a year. And the reason why you don't know much about direct products of it is that essentially the aldehydes are used as feedstock materials, right? So they're used to make other things and lots of other things. And so what often happens is the aldehydes are then hydrogenated to an alcohol. And that can be used for plasticizer or detergent or other types of things that you do use every day. Another reaction that is very useful for this is that this basically is a way to introduce stereocenters. So sometimes they use chiral groups on the catalyst to induce the stereochemistry that's desirable. And so, for example, when I was looking at this hydroformylation using chirality and introducing stereochemistry is using the synthesis of ibuprofen, right, which is something you use every day. So there are 2 common catalysts that are used for this reaction, and one of them is a cobalt catalyst, and one of them is rhodium, which is right below cobalt. So not surprisingly, they have similar reactivity. The rhodium one is more active at lower temperatures and pressures. The cobalt one is obviously cheaper than rhodium. It's a more abundant metal. But I'll go through the cobalt one right now, and the rhodium one is also in your textbook. So this, what oxidation state is a cobalt in?
+1.
+1. How many electrons is it?
D8.
Complex electron count. Somebody else?
18.
Huh?
Is it 18? No.
Are you guys guessing? I'm asking. You don't have to check, but obviously you were very confident in your answer. You weren't in check. Is it? Now you're more confident?
I'm pretty sure it's 18.
It is 18. It is 18 electrons. Okay, so it's 18 electron compound. This step, losing a CO. What happens when you lose a ligand? What is that called? Ligand dissociation. That's a reaction that we've discussed. Right, so you end up with H cobalt CO3. you're still cobalt-1, right? You haven't changed the oxidation state, but now how many electrons is this complex?
16.
16, right, 16 electron compound. So it's a little bit more reactive in this case, which is what you would expect for a 16 versus 18 electron compound, once you lose that carbonyl. So then you add a alkene. I'll just drop the double bond here. And you make a alkene complex. Right, and you know how that can interact with the metal center based on the orbital overlap. And this one can now do, let's see how to draw this. I'll put the carbonyls on this side. 2 H H C H R R. So what happened here? Oh, brought right over with me. Is that you have. So what kind of insertion reaction is this? 1,2 insertion, right? This is a 1,2 insertion. And this is how many electrons? So we skipped one. So this one, when we put this ligand back on again, how many electrons is this one? 18, right? Because the ethene is a 2-electron donor if you're doing a covalent or ionic model. This one is now 16 again, right? So it's alternating between 16 and 18 electron species. This insertion reaction. What happens is then you get CO addition, so it's an addition, ligand addition reaction to make, let me draw this out again. CrRH, cobalt 3, to make another 18 electron compound again, so it adds CO again. So what happens then is a CO inserts into this bond right here. One of the COs inserts into this bond. And you end up with this. Of course, that H is still there. That was originally part of the hydride, that hydrogen, but it's not really. So if there's R's or H's, it's just a methyl group at the end of it. So this is the one where, just remember that you can either call this an alkyl migration or a CO migration. And if you remember when we started looking at this reaction at first, it's actually hard to tell the mechanism. It's sort of subtle, it's sort of which one moves. Does the CO move into the metal carbon bond of the metal alkyl, or does the alkyl move into the metal CO bond? So you can usually call it alkyl or CO migration. It's fine, either way. This one is now, how many electrons? It's got 4 things around it, that helps, probably. 16, right. So one's now 16, so you're alternating between the two 16 and 18 electron species. Add hydrogen. So when you add hydrogen, what kind of reaction is this? So the first thing you can sometimes ask is whether the oxidation state changes or not between these two species.
Yes.
They're both neutral, yes. And so How does the oxidation state change? What's the oxidation state of this? Somebody that hasn't been answering on this side. What's the oxidation state of this? You can guess, everyone else guesses. What's the oxidation state of this one? 0. It's neutral, but this one's actually a -1 charge. So, +1, right. Okay, and this one, so this one is still a -1 charge, but now you have these two hydrides on either side. What's the oxidation state of the cobalt? +3, right? So the cobalt has been oxidized or reduced? It's been oxidized, so what's this reaction? Oxidative addition, right. It's not hard. You guys know all this stuff. Okay, so then what then happens, so you have oxidative addition to add hydrogen to this species, this intermediate, and then what happens, and I'm just sort of picking one of the hydrides, it actually, you know, they're both equivalent in this case, but what happens then is that you go back to your starting material, and the way that you do that is you basically lose, I'll put a minus here, so this is the product that you're losing. 2HC, CH2COO. Alright, so you started with an alkene. I'll use another color. You started with this alkene, and then now you have the aldehyde, right? So that's how the catalytic cycle goes. And then when you lose this, you end up getting right back to here again, right? Because, well, you have to add a carbonyl. But basically, you could also look at it as going back to here, I guess. You go back to this part of this catalytic cycle, or you could add a carbonyl, go back to this one, and then lose it again to go there. But essentially, you get back to the resting species of your catalyst. So what's this called when you lose those two groups? What's the oxidation state of, well, I guess you're losing it to there. Although I guess it doesn't matter for your oxidation state. You're actually, if you're going to be very rigorous about it. The oxidation state of this one, it's +1, right? And this one is 3, so what happens to the metal? Right, so it's a reductive elimination. So from the metal's point of view, when you do an oxidative addition, you're gaining 2 new bonds. And that, yes?
I'm confused about like the step on the far right.
Okay.
What did you do to add 18 electrons and not show the formula?
Yeah.
Which one? This one?
Yes.
You
Okay.
have 3 on top and then you still have 3 CO groups attached
Oh,
to the
did I lose?
cobalt.
Oh, did I not?
Should be CO4.
I'm adding this one? Okay, sorry. Thank you for pointing that out. If I make typos on the board, please let me know. So yes, that's true. So essentially, when you do oxidative addition, you oxidize the metal center by 2 electrons, and then you form 2 new bonds to the metal center. When you do reductive elimination, it's basically the reverse of that, right? You're reducing the metal center by 2 electrons, and you're losing those 2 bonds, because they're basically coming together to make something else. In this case, this, right? You need to make that, you need to add a proton to this aldehyde to make it come off, and to make that new bond. So you take the electron to the metal center. Okay. So yeah, so rhodium is also used for this reaction. Like I said, it's the largest one that's done industrially. In some cases, rhodium is actually more cost effective, even though it's like, I think it's like 1,000 times more expensive per ounce, but it's so much more active that you're able to work at lower pressures and temperatures. And you know, when you work on million-ton scales, that's a big deal. Being able to work at lower temperature pressure means that your reactor can be made, you know, to withstand less pressure, and so the overall cost ends up being lower using rhodium often. Additionally, you can also recycle the rhodium catalyst. So that's, I think nowadays they almost always use rhodium. So they started using rhodium because that was the first one discovered. Then they found cobalt could also do it, which is sort of a natural, to look up in the periodic table, right, because they are in the same row, or the same column. But then I think they found that it doesn't really match the activity, so now people have gone back to using rhodium for the most part for this reaction. So another process is called the Wacker-Schmidt process. This one's also discussed in your book. So this one, the overall reaction, is taking an alkene. Alkenes are a very common starting material because it's one of the most common groups found in petroleum, so if you can find ways to functionalize, that's our major source of carbon right now is petroleum or oil type, fossil fuel type sources. This also takes the alkene to an aldehyde. One of the reasons why this is sort of an interesting reaction to a lot of people is that you're basically taking the oxygen from water to incorporate into this aldehyde. The other thing is that it is an oxidation reaction, so the reason why this is sort of a significant reaction is because it uses oxygen as an oxidant, which obviously is very plentiful. You don't have to use bleach or hypochlorite or other hydrogen peroxide or other kind of nasty chemicals to do your oxidation process. So you guys should be very familiar with this type of ligand complex, right, with an alkene as a ligand. It looks like Zeiss's complex, which you probably don't remember, but it was one of the first things we talked about when we started talking about organometallic chemistry. It looks a lot like a compound that was first isolated that had a metal alkene bond associated with it. This is an overcharge of minus, that's 2 minus, this is now 1 minus, because you lost the chloride, and added a neutral ligand to it. If you add water to this, so you will replace the ligand that is trans to ethene with water. We lost another chloride. So this is one of those situations where I told you that one of the things that is very interesting about metal aromatic compounds is that you've basically activated that carbon for attack, which a lot of times would not happen otherwise. You basically, by adding electron density, if you remember that an ethene is a sigma donor, right? We had this on our quiz. And that basically takes away electron density from a bonding orbital. And also, it does a pi donation from the metal to the anti-bonding orbital in the ethene. So basically, it weakens this interaction. It basically destabilizes this molecule and sort of activates it for reactivity, right? Which is great when you want to actually functionalize it, is that you want to be able to find ways to make it more reactive. So what happens here is a water does nucleophilic attack onto one of that carbon. And this is not something, if you just mix water and ethene together, nothing would happen. But this is because of that interaction. You're able to weaken this carbon for attack. And the result you get is the alcohol. So you end up losing one of the protons off the water, and you get the alcohol out from attacking the ethene that's bound to the I guess it's palladium, not platinum. I haven't written platinum, did I? No, that's why I wrote palladium. Good. Okay. And then there's a reaction that we haven't really talked about much, and I don't expect you to know off the top of your head, but you get intramolecular elimination which is an elimination reaction that happens not at the metal center, so the oxidation state doesn't necessarily change, but within a single ligand on the metal. So intermolecular elimination to get and then you get palladium 0 plus the 2 chlorides that you've lost in this whole process in order to get this aldehyde, which of course gets deprotonated. And so in order to get back to your starting material, you basically, this of course deprotonates, that's not a very stable species, it's very, very acidic, and so it'll deprotonate to give you your aldehyde. Plus an equivalent of acid, right? Because it'll separate. It's acidic in solution in order to regenerate. And so one of the things that is very interesting about this reaction is that you end up with a palladium 0. You can't. This was not a palladium 0 to start with. Of course, it's palladium 2. And so the way that they're able to oxidize is by using copper chloride is usually added to the solution to reoxidize. Because that's a favorable reaction, right? So if you look at the redox potentials of copper chloride versus palladium chloride, you'll see that it's favorable for copper to be reduced and this to oxidize back up to palladium 2. But the interesting thing about this reaction is that this can then be turned over with O2, right? So then you make copper metal, copper 0, but then that can be oxidized in air back to copper 2 again. Which is why this reaction is sort of interesting because it's considered a very green way of making aldehyde because you can use O2 as your oxidant. In the reaction versus, like I said, something like hypochlorite or peroxide or things that are not as good for the environment. So this is sort of the mechanism for this reaction, which is pretty important. And like I said, I don't necessarily need you to find your own mechanism for things or memorize any mechanisms. I just want you to be familiar with the types of steps that can happen along the way in a known mechanism, whether or not they're reasonable or not, based on what you've already learned about that. So the last thing, is this the last thing? No, second to last thing, is in your chapter they talk about olefin metathesis. This is was on your homework problem, but hopefully you didn't have any problems since it's in your textbook as well. So if you have 2 different olefins and you mix them together in the presence of the appropriate catalyst, then they will basically isomerize into the different combinations of those catalysts. Right. So this was discovered in, I think, the 50s or 60s by at least 2 different people and one person that proposed the mechanism, and I think the 3 of them won the Nobel Prize 2007, it's my first year of grad school, for basically discovering this reaction, and it ended up being very important, or 2001, that was my first year of grad school. So this is a very important reaction also for synthesis in order to make mixed alkenes, because if you think about all these reactions, you're basically unsaturating the alkene bond, but this is sort of a, so you're unsaturating the alkene bond, but how do you get to materials that have the right R groups on either side, right? Because you can find ways to functionalize your alkene once you have the R groups that you want on it, but how do you get to the ones that you want? And this is one of the ways that you can get to alkenes that are desirable. So the proposed mechanism is essentially formation of a carbene from one of the alkenes. So basically you cleave one of the alkene groups, one of the alkene groups into making 2 equivalents of the metal carbene. So I'm going to put the R in a different color, R prime in a different color, so you can see where it goes without just showing it as R prime. Okay. CHR. And essentially, you form something that you have seen several times throughout this chapter, which is a metallocycle butane, or metallocycle, which we've talked about a little bit in different compounds. This one is R prime. R prime. Follow where it goes. H2, CHR. Right, so this is a metallocycle butane. Intermediate, which can then separate out. So essentially you break two bonds and you make two new bonds, right? So you're making these two new bonds. You're making these two new bonds, and then you're breaking these. So what you're left with is a new carbene plus a new alkene. Now you see where the R prime has gone. It's gone on to a different group, right? So instead of having okay, right. So now you have a different carbene that you can start with, and now this can then mix with another alkene and then isomerize with that, right? And basically go through this cycle again, where you basically can scramble groups with different groups that have different sides of an alkene, different functional groups across the alkene. So an example of this is if we start with this plus this, what are the different things that we can get? So we can think about the different groups. If we think about what each carbon has on each side, we have a CH2 on this side. We have CH2, CH1, CH3. We have a CH2 again on this side, right, of this alkene, and then we have a CH2, CH3. So you basically can think of every combination of that as you can think of putting these two together, of the different products you can get. So that includes just this, right? So you have CH2 on either side. If you try to do, for example, CH2, CH3, this combination, you end up just getting this one back again. So it's not, I mean, you can call it a product, but it's not really, you don't know if it was what you started with or something new. It's not anything new that you made. So that one would not be considered new, but other new ones that you would get are this one, which is having this twice on it. You can get this one, which has that twice on it, and then you can get a mixture of these two. Right. So it's sort of just like one of those games that you can play where you mix things together and you see whether or not what the new scrambled products are for everything. And that's olefin metathesis. The same thing can happen with alkynes. Instead of a carbene intermediate, you have a carbine intermediate, right? The metal triple bond. So we'll try to do this in different colors again. That helps you keep track. Red is dying. You form another metallocycle intermediate, except now, of course, there's a double bond and a single bond to a carbon. It's sort of the analogous reaction, except you just have to change some of the bond orders to keep them consistent. You don't lose electrons that way. This one is R prime. So it's very similar. If you understand olefin metathesis, you understand alkyne metathesis. It's the same thing, except instead of making new alkene derivatives, you make new alkyne derivatives. And instead of having a metal carbene intermediate, you have a metal carbine intermediate. And yes.
If you're running this reaction and you want one of those products, but you have a mixture,
Uh-huh.
is there any way to increase the yield of one? Because it seems like you would get really terrible yields.
Yeah, I don't know the answer to that question. I would imagine that they've done work on that, or maybe if there's like something that's more volatile that you want, you can maybe basically pull it out as it goes, because it'll basically keep isomerizing in solution. And so if you're able to separate it in situ, then you're able to drive the equilibrium toward the one that you want. But that's a speculation on my part. I actually don't know. So the last thing is heterogeneous versus homogeneous reactivity. So basically on Monday, I'm going to be talking a little bit about heterogeneous catalysis, just because we haven't had the opportunity to. Obviously, it will not be on your midterm, and they don't talk about it very much in the book, but I just wanted to go over that a little bit, because the vast majority of chemicals that are made with heterogeneous catalysts. We tend to study homogeneous catalysts more, so that's why all of our studies and mechanisms are with homogeneous catalysts. So this is usually cheaper and more stable, because they tend to be like something like a copper surface, or actually a lot of what they use to refine oil, to do catalysis to refine oil and petroleum products are zeolites, which is basically clay, right? It's like it doesn't really get any cheaper than that. They can use different clay products that has trace minerals or trace metals in there that can do the catalysis that they want. And of course, a lot of times they have to get it from a certain region. There's certain kinds of clays that are better than others, but it doesn't really get any cheaper than that, right? But the advantages that homogeneous catalysts have is that they have higher selectivity for products, typically. If you are doing pharmaceutical catalysis, like making ibuprofen, and you need a chiral center, they tend to be better with homogeneous catalysts, because it's obviously easy to make molecules that have chiral centers that are, the ones that you want. And there are some studies now that are trying to make surfaces chiral by inducing designs onto them that make them basically handedness, so that you can do an antioselective catalyst onto a surface. But right now it's sort of not as developed as in homogeneous systems, which is much easier to characterize. And the biggest advantage of homogeneous systems is that they're easier to study, and learn about mechanism. Because in the end, if you want to improve a heterogeneous catalyst, they don't know a lot about what happens in the mechanism, so it sort of gives you no good starting point of how to improve a catalyst. Whereas now we've looked at all these mechanisms, and we can say things like, you can learn about what the rate determining steps are, what are the different procedures that happen in them, and how do we improve it, how do we add chiral centers to be most effective, and the important step that adds chirality, that makes something prochiral into something that is chiral. And some of the reasons for this, so I know a lot of you haven't done undergraduate research, but you know that in NMR and other techniques that we have, you can make a solution that's pretty easily millimolar, and that makes it very easy to study. Whereas on a surface, the actual concentration of things on a surface is usually like picomolar, right? So it's like, I don't know, I guess that's like 6 or a 9 orders of magnitude off. So they just don't have a lot of instruments that are sensitive enough to detect things like intermediates and things on the surface. So it's really hard to find the mechanism of what's going on, although that's getting better every year. People are always developing new techniques for that. So one of the processes that is very important on a large scale for heterogeneous catalyst is the water-gas shift reaction. We talked about this, we talked about CO chemistry, I think. So basically this reaction takes CO, which is usually made by gasifying, CO, which is basically made by gasifying coal usually. And then they are able to oxidize the CO. Oops, that's H2O, yeah, H2. So they oxidize the CO, reduce the water to make hydrogen. So this is how most of the hydrogen is made in the US right now, is using this water gas shift reaction. And so one of the goals, so the catalyst, sorry, that's the same. The catalyst that's used for this is usually an iron or chromium surface or a zinc copper mixture at high temperature. And so these are heterogeneous catalysts, right, because they're just solid materials. And the question is, how does this reaction work? And so there are several inorganic groups out there that try to basically replicate reactions that are done in heterogeneous systems using a homogeneous system, with the understanding that it may be analogous in terms of mechanism, but we can actually study the homogeneous system, but we can't study the heterogeneous system for mechanistic details. So this one, you start with a ruthenium bipi system. You add carbonyl minus halide, so you end up with ruthenium bipi, CO with one Cl, right? So this is the ligand substitution reaction, and then we basically do it again, except you add water and you minus the Cl. It's water. More clearly. This is another ligand substitution reaction. How to do this? Okay. And then you get to the resting catalyst, or the active catalyst. Once you add CO and water and you get rid of both chlorides, you get to the active catalyst. Which is this ruthenium 2+ species. Because all these ligands are neutral and the total charge is 2+. And you add carbonyl, subtract water to get to B2CO2. You haven't changed the oxidation state, you're just doing ligand substitution reactions. These are all very first thing that you learned. So what happens next is you get a hydroxide attack onto the carbonyl, which again is something that wouldn't happen unless it was coordinated to a metal. This is a nucleophilic attack on the electrophilic carbon on the ruthenium carbonyl complex. OOH. Right, so you get a carboxylate because you had a hydroxide attack onto the CO, and your end result is a carboxylate ligand. This is now 1+, so you haven't changed oxidation state at all. These are all reactions that are happening without a change in oxidation state of the ruthenium center. You then get a ligand elimination, so we talked about that a little bit before. It's not one of the reactions that we've really studied a lot, but essentially you're not eliminating off the metal, so the metal oxidation state doesn't change. You're basically eliminating off this ligand, the carboxylate ligand, because I don't know if you remember in organic chemistry, but sometimes when you have like aryl carboxylates, they'll decarbonylate. And so this is basically a decarbonylation of this ligand, where decarbonylation gives you, a CO2 coming off of it. So you end up with the hydride, 2CO, so you still have one CO. And you guys remember metal hydrides from when we first started doing organometallic chemistry. And then essentially you get water in the form of, well, it's basically acid. I guess you're in water, so it's H3O+, but you basically get acid addition. So one of the reactions that you knew can happen with hydrides is protonation of a hydride to make hydrogen. So you lose H2. So you add H+, you lose H2 to this metal hydride, which is a reaction that you're familiar with. And so the end result of this catalytic cycle with this ruthenium compound that's been looked at is you add CO plus OH minus plus H plus, right? Later in the cycle you get H plus in the form of H3O plus water, to give H2O plus CO2 plus H2. Sorry, there's not H2. Plus CO2 plus H2. Those are the two products. Of course, this just gives you H2O because they're basically, conjugate acid and base. Freshman chemistry. CO2 plus H2. So this basically mimics the water gas shift reaction, and it sort of allows us to study what's probably happening on the surface, because it's sort of reasonable to expect that if in this ruthenium compound, once the CO is coordinated to the metal, it becomes much more electrophilic, and it becomes subject to nucleophilic attack by hydroxide to make a carboxylate, that this can then decarbonylate. So it gives us sort of an analogy of what's probably happening on the surface, and that is very helpful when you're trying to improve catalysts, as I said, because then you sort of understand what the different reactions are, and then if you do kinetics on it, you can understand which is the rate determining step. And for example, if this attack is a slow step, how do we make this carbon more electrophilic, right? How do we make this attack faster? If the decarbonylation is the slow step, how do we make a stronger hydride, right? Because that will drive the reaction forward if we're able to stabilize this intermediate. And so this is sort of the reason why we try to find analogies to heterogeneous reactions with molecular compounds, because it allows us to study, because we understand the reactivity of them more, and we have more tools to study, which is the important part, right? Because if you can't see it, you don't know what's going on. And in a lot of heterogeneous systems, you can't really see what's going on, at least on a macroscopic scale. So that's the last reaction. You guys have questions about, it's going to be on the midterm, it's those 3 chapters that we've covered, everything we've done so far. Like I said, you don't have to memorize mechanisms, but I want you to know what the different reactions are and how to identify them in a catalytic cycle. Yes?
What will we be given?
What?
What will we be given?
So for the trans effect, I will give you the series, because I don't want you to memorize that. And I will probably put the periodic table up on the projector, even though you guys should all know it by heart. But that way you don't have to have an extra thing to think about, I guess, when you're doing your exam. The other thing is that I'll try to get in early and mark the desks, but when you guys come in for the exam on Friday, try to sit one apart from each other. We should have enough seats in this room. I think I counted last time that we should have enough seats. If for the 3-row ones, if people sit on the corners, so no one sits next to each other. If you take most advantage of the space, we should have enough room for everybody. Yeah, but that's what we've provided. Any other questions about what's going to be in the exam? Okay. All right. You can bother Zach if you think of other things.